false? A is diagonalizable if and only if A equals PDP inverse for some diagonal matrix D and invertible matrix P. True. That's the definition of diagonalizable. So that means that you can factor, you can rewrite A as the product of three matrices, one of which is a diagonal and one of which is invertible. Has to be invertible because P inverse is part of the formula. That's IFF stands for if and only if. Yeah. Only if. That's a mathematical shorthand. If. Yes, in a logic, in logic courses, you see the same thing. Okay, if D is 2003, find D to the fifth, no calculator. Yeah. So in a diagonal matrix, raising it to a power is really quick. It's just 2 to the fifth, 0, 0, 3 to the fifth. And if you put a 32 and a, what's the other one? 243, good. If you wrote that, good. If you didn't know that shortcut, you would have had to multiply D times D times D times D times D. Would have taken you much longer, right? Okay. True or false, an n by n matrix with n distinct eigenvalues is diagonalizable. Yeah, that's true. That's a theorem from the text. So today we're going to learn how to factor a matrix in a special way. And it's a way that's really useful for making large computations quicker and easier. So we're going to see one brief example of a computation that's made easier by this special factorization. But there are many, many, many more things that will be made easier by this diagonalization factorization. It's a powerful tool. You'll probably see it again in another engineering course or in a differential equations course. But we are not going to apply it again in this class. But just because that doesn't happen, I don't want you to think that it's unimportant. So we are covering it because you will probably run into this again in some kind of advanced class. So think about like when you were first learning how to factor polynomials. You spend a ton of time learning how to factor polynomials, and it's kind of hard at first. And you don't know where it's going. You don't know why you're learning to do this thing where you write a polynomial as the product of two things, right? So it's kind of similar to that. We're going to rewrite a matrix as the product of three other matrices, and like why we're only going to do one small example of a computation that's made easier by this, but there are lots of them. Okay, so a diagonal matrix is a matrix that has zeros everywhere except the main diagonal. We already knew that, just a reminder. So the definition of diagonalizable is a square matrix that's similar to a diagonal matrix. So we talked about similar last class, and it means that you can write it as PDP inverse. So A and D would be similar in that case. An n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. So the n linearly independent eigenvectors make up the columns of the matrix P. So if you're trying to diagonalize something, if you know its eigenvectors, if you can come up with n linearly independent eigenvectors, that's your P of the diagonalization factorization. And the corresponding eigenvalues make up the diagonal entries of D, the diagonal matrix. So you know eigenvectors, you know eigenvalues, then you can do this factorization, diagonalization. And a matrix that has n distinct eigenvalues is diagonalizable from the theorem above, right? So if you can come up with n linearly independent eigenvectors, then it's diagonalizable. And if you have n distinct eigenvalues, eigenvectors associated with the distinct eigenvalues are linearly independent. We saw that in the previous couple of classes. So if you have n distinct eigenvalues, you will most definitely have n linearly independent eigenvectors. But this is sufficient, but not necessary. You could still have a matrix that's diagonalizable, even if it has fewer than n distinct eigenvalues, just not always. All right, so the steps to diagonalize an n by n matrix A is find the eigenvalues, use the eigenvalues to help you find n linearly independent eigenvectors of A, and then construct P using the eigenvectors and put them in any order, and then construct D by putting the eigenvalues on the diagonal entries. And you just have to put them in the same order that you wrote the eigenvectors. So the eigenvalue that corresponds with the eigenvector of column 1 should go in the first spot of D. All right, so diagonalization makes a lot of computations easier. You'll probably see several in upcoming courses, but one such computation is raising a matrix to a power. So if D is a diagonal matrix, raising it to a power is really easy. You just raise the diagonal entries to that power. It's a lot easier than raising a non-diagonal matrix to a power. So we use diagonalization to help us make raising a non-diagonal matrix to a power. If you can factor it into P, D, P inverse, then raising a to the K, which is not a diagonal matrix, raising that to the K is just going to be P times D to the K times P inverse. So if I wanted to do, say, A to the 14th, right? If I wanted to do that in the standard way, I'd have to do A times A times A times A, which is 14 matrix multiplications, which would take a long time. But instead, if A is diagonalizable, I can rewrite it as P, D, P inverse. And then D to the 14th is really easy, right? And then I must just have to do 3 matrix multiplications. So this would save a lot of computing time. No, sorry, no. You can linearization is a real thing, and we talk about it in differential equations, but it usually is not good globally, only locally. Like if you think about Calc 1 where you linearize, yeah. You can do that in other contexts, but it still is usually only good locally. Okay, and then the last theorem says that if you have an n by n matrix that has p distinct eigenvalues, the dimension of the eigenspace for each eigenvalue is always less than or equal to the multiplicity of the eigenvalue. That was an exercise from your homework from last class. And a matrix is diagonalizable if and only if the sum of the dimensions of the eigenspaces is n. So if you find the dimension of each eigenspace associated with each lambda, they have to add up to n for it to be diagonalizable. And if A is diagonalizable, then the collection of all the bases of the eigenspaces of A forms what we call an eigenvector basis of Rn. That is, the columns you use to form P when you're doing diagonalization, those are going to be the bases of your eigenspaces. Those will be linearly independent and span Rn, which means they are a basis for Rn. Diagonalizable. You would count, okay, so you count it, you would say, like, let's say lambda equals 4 is multiplicity 2, right? You'd find a basis for lambda equals 4. That basis will always be less than or equal to the multiplicity of the eigenvalue. So its dimension will always be less than or equal to the multiplicity of the eigenvalue. So if there are 2 vectors in its basis, then it equals the multiplicity. And that has to happen in order for A to be diagonalizable. If you have an eigenvalue that has multiplicity greater than 1, the number of vectors in the basis of that eigenspace has to be the same as the multiplicity in order for A to be diagonalizable. We'll see an example. Because I know, because if you're trying to come up with linearly independent vectors, We'll see an example. I don't think that it's going to be clear if I just keep talking. Okay, so here's a matrix that's already been diagonalized, right? So I rewrote A as a P times a diagonal matrix times a P inverse. Okay, so some invertible matrix, it's invertible because its inverse is over here, times a diagonal matrix times P inverse. So you could check if you want to type those all into your calculator, multiply them together, you do get A. I'm not telling you yet. Well, it's in the notes how you come up with P and D. So P is eigenvectors of A. So P is made up, you need to create a P, which is not necessarily distinct, right? It's not, or unique, it's not unique. But to create P, you need n linearly independent eigenvectors of the matrix A. That's how you make P. Those are its columns. Nope, I gave you the original matrix too. I'm going to ask you some questions in a second. All right. And then the diagonal matrix D is made up of the eigenvalues that correspond to the eigenvectors you put in P. All right. So knowing that, what are the eigenvalues of matrix A? 3, 6, and 6. Right. And in this case, 6 appears twice in the diagonal matrix D, so it is a eigenvalue with multiplicity 2. All right, so if I wanted to give a basis for each eigenspace, right, so the eigenspace associated with each of these eigenvalues, so let's consider lambda equals 3, the eigenspace for lambda equals 3. So 3 is in the first column of D, so the first column of P is a basis for the eigenspace for lambda equals 3. So it would just be 1, -3, -1. Or any scalar multiple of that vector would also work, which is why P is not unique. Yep, the basis for the lambda value for the eigenspace of lambda equals 6, because it shows up in these two columns, these two vectors of P, the second two columns of P make up the basis of the eigenspace. Yep. So let's see, this is 0, 1, 1, and 2, -1, 0. So Todd, this is what I was trying to say earlier, that if you have a lambda value that has multiplicity 2, there have to be 2 vectors in its eigenspace in order to create 3 linearly independent vectors with which to build P. Because if 6 only had 1 vector in its eigenspace, I could only come up with 2 linearly independent eigenvectors. I wouldn't be able to build P, so we would say A is not diagonalizable. Right. Because it's the second 2 columns of P, because 6 is in the second and the third column of D. So, oh, okay. All right, so what is this factorization good for? In order to write this factorization, if you have the factorization already, it's nice because you can pull out the eigenvalues and the eigenvectors. If you were trying to diagonalize something, you would have to figure out the eigenvalues and eigenvectors first in order to write it like this. But that effort is sometimes worthwhile to make calculations like a to the 4th easier, right? So a to the 4th, this is a 3 by 3 matrix, a times a times a times a. I'm going to have my calculator do it. Because, or actually, maybe I'll just write out what it is first. Okay, so there's A. All right, so if I wanted to do that by hand, it would be a lot of multiplications. That would be a lot of computations to do by hand. So as my calculator is pretty good at this, I'm going to have it do it. But even if I had wanted to do, say, instead of a to the 4th, like a to the 50th, this would take your calculator a long time to do. That's just a lot of computations. So while we're just learning how this works, we're going to do just to the 4th, but the idea behind this is anytime you're doing numerical computing on a computer, you can save a lot of time, running time in your program if you use a diagonalization. All right, so let's see, we've got 7 to -2. Oops. Oops. 2, -2, -3, 0, 6, and -1, -2, 8. So then I'm just going to do matrix A to the 4th, and it gives me a result. All right, you can't see the whole matrix, but we'll get a good idea if we did it right from the first few entries. Okay. So now if I want to do it using my shortcut, I can do a to the 4th is the same thing as doing p times d to the 4th times p inverse. And p up here is 1, -3, -1. 0, 1, 1, 2, -1, 0. So there's p. And then d to the 4th is really easy. You just take the values on the diagonal d and raise them to the 4th. So, yep. What? No, so think about all the different computations that have to happen to multiply these together. You have to do each row times each column. So just doing this times this is 3 multiplications and 2 additions, right? And then you have to do that for each row and each column. So we've got, yeah, there's a, what?
Well, I'm thinking like, if you're reading.
Yeah. Okay, so then times p inverse. Yeah, p are the columns of p are any 3, because it has to be 3 by 3 in this case because a was 3 by 3. Any 3 linearly independent eigenvectors of A. So you have to get eigenvectors of A. Pick any 3 linearly independent ones. They make up your columns of P. And then the entries in D are the associated eigenvalues to those eigenvectors. And then P inverse, you just take the inverse of P. So -1/3, -1/3, 2/3. -2/3, -2/3, 1/3. -2/3, 5/3, -1/3. So now I just have to multiply 3 matrices together instead of 4, right? So I saved myself 1 matrix multiplication, which has actually a lot of computations within it. And if I was doing a to the 50th, this would save me a ton of time. Yeah, so this is a way of shortening the computing time, whether you're doing the computing by hand or programming a computer. And it became more important when we started using matrices to model real life things. Like when you might have 1,000 equations with 1,000 unknowns making up a huge matrix A, and then if you want to raise a to the 50th, that like it would just take too long. The computer couldn't even do it, right? So it became important to try to come up with some little trick to make raising a matrix to a power faster.
Now, what if A is like constantly changing and rotating? Would B be correlated the same?
No, every time A changes, you would have to come up with a new diagonalization for A.
So this wouldn't work for something like practice.
I'm not sure. I'm not sure if that's a place where it would apply or not. I don't know. Okay, I'm gonna let you guys do some stuff now.